Hello everyone. Let's continue our discussion on optimizing the placement condition, and once we are done with the placement optimization step, the next step is to do a quick timing analysis with ideal clocks. Basically we need to do a timing analysis with the existing placement op condition. Okay, so let's begin. We already finished, we already discussed a bit about the placement optimization for this set of logic. Let's try to cover it even more in more detail over here. So you have this particular buffer which was placed, and the reason this buffer was placed was D in 2 was at a significantly large distance from flip-flop 1. Okay, so whatever D in 2 speaks, FF1 is supposed to hear it in the same condition. So in order to reproduce what D in 2 has sent, or in order to reproduce the signal that D in 2 has sent, we have placed this particular repeaters in the center. Okay, so these repeaters will take the signal from D in 2, repeat it or recondition it, or basically reproduce the same signal and send it again. This buffer will again reproduce the same signal and then send it again. So in this case, whatever signal conditions was there at D in 2, that will be getting faithfully reproduced at flip-flop 1, at the input of flip-flop 1. Okay, so that was the purpose of adding these two buffers. Next, when we move on from flip-flop 1 to the next logic, or which is this particular gate, since these two are sits very close to each other, there might not be any problems for reproducing the signal that is being generated by flip-flop 1 and send it to the logic 1. And the same condition exists for the connection between 1 and 2. So basically this is called as abutment. We have abutted certain logic so that there is actually no time delay between the signals which is getting passed from this point to this point. Okay, and there are multiple reasons to do this abutment. The one of the reasons is, let's say this particular section of your circuit works at very high speed. So in that case, what we do, we bring those set of logics very close to each other and make sure that there is absolutely zero delay when sending the signal from flip-flop 1 to flip-flop 2. Okay, so let's say this works at 2 gigahertz or something. So in that case, we don't want to waste delays on the wires, and as a result of that, we have abutted this particular cells. So this is a very classic example of high frequency circuit. Next, the flip-flop 2 has got some signal which is sent out to D out 2 with a minimal delay, with a minimum delay. So the wire delay from flip-flop 2 to D out 2 will be wire length will be very less, and as a result of that, the delay will be very less. So this piece of logic looks to be taken out of a circuit that is working on a very high frequency. Okay, next, moving on to the next set of circuit. So let's say we have this blue colored circuit. So blue colored circuit, we have the D in 3, we have D in 3 over here, and we have D out 3 somewhere over here. Okay, so let's look into the conditions. So D in 3 is placed at a sufficient distance from flip-flop 1. We might not need the we might not need a repeater somewhere over here because it's a reasonable distance to reproduce the signal, and these conditions are being calculated based on the transition value or based on the slew value, which we'll be talking about once we finish the optimized placement. Basically, once we move into timing analysis for ideal clocks, we'll talk about what is the acceptable marginal condition for the signal to be considered as a real signal, or as a sufficient signal to trigger the flip-flop 1. Okay, we'll talk about that. So D in 3 to flip-flop 1, we might not need any buffers. Flip-flop 1 to 1 also we might not need any buffers because this looks is sufficiently less distance or reasonable distance. From 1 to 2, we also might not need any buffers because looks like it will be able to send the signal faithfully to the logic 2. Okay, from 2 to flip-flop 2, it looks a bit high, the distance looks a bit high based on the analysis that we will be doing sometime from now. Based on the slew analysis or the data transition analysis, looks like the distance between 2 and flip-flop 2 is a bit high, so we'll place a buffer over here. And now the distance between 2 and buff is one of the distance, and from buff to flip-flop 2 is another distance. Okay, and finally we have the flip-flop 2 that moves to D out 3. So you have flip-flop 2 to D out 3, which also is placed sufficiently close to D out 3, and hence we don't need any buffers in this area. Okay, next the final logic we have. So we have D in 4. This is a bit tricky. Let's see how do we solve it. So D in 4 is placed somewhere over here. Okay, and D out 4 is placed somewhere over here, and you have and the signal has to traverse right from this point till this point. Let's do that. So from D in 4 to flip-flop 1, the distance looks a bit high. It looks a bit on a higher side. Okay, so you need to place some buffers, and you can't place buffers in this area because this part of the floor plan is already occupied by decoupling capacitors and blocks and so on. So you can't place a buffer in this area. Let's try to route it, or let's try to place the buffers from this path. So we'll add one buffer over here, and then now the distance from D in 4 to buffer looks significantly less, and looks like the D in 4 signal will transfer to buffer input with the same slew conditions. Okay, moving on from buffer to flip-flop 1, it still looks okay. We don't need any extra optimization to be done in this area. From flip-flop 1 to 1, this distance also looks okay. The only problem that we see over here is there is a kind of crisscross. Okay, so you have buffer to flip-flop 2 over here, you have flip-flop 1 to 1 over here, and these are very normal conditions in a placement and routing tool. We will be taking deconnecting this flip-flop 1 to 1 in a separate layer. We'll be trying to connect this buffer to flip-flop 2 in a separate layer. So we'll talk about a bit of placement and route algorithms, not in this section but in a separate section. We'll talk about that in some time, in a few slides from now. So we will so there are crisscross, but we will find out a way to fix this in a routing stage, where we take this connection from this point to this point in a separate layer, let's say metal 3, and we take this connection from this point to this point in a metal 4. You can think currently you can think of it in that it will be a different layers. Okay, next we have this connection from this point to this point. Again, if you see, the distance is a bit high, and also there is a logic which is sitting over here, and this again a normal condition. And the way the routing might happen is the flip-flop 2 is in the internal routes of the flip-flop 2 might be in some layer, let's say metal 1, metal 2, and the connection from the signal connection from 1 to 2 will be on a separate layer, that will be like metal 3 or something of that sort. Okay, so this distance still looks a bit high, so let's place a buffer over here. Okay, and then now let's route from 1 to buffer and buffer to 2, and finally from 2 to you have this flip-flop 2, and then flip-flop to D out 4. So we have done a significant amount of buffering in this area, and all basically complete logic is being now optimized based on the placement condition. Okay, so next what we have to do is we have to check what we have done is correct or not. So for that, now since the clocks are not built, what we have to do is we have to just check the data path over here. So considering there are no clocks, or considering the clocks are ideal, by ideal clocks we mean that the time required for the clock 1 to reach flip-flop 1, flip-flop 2, any of the flip-flops is 0. So based on the ideal conditions of the clock, let's try to quickly do a timing analysis. Okay, a setup timing analysis, a hold timing analysis, and not hold, basically. So hold will not make any sense once we don't have the clock. So let's try to do a quick setup timing analysis with idle clocks. Okay, and based on the setup timing analysis, or based on the numbers that we get out of the setup timing analysis, we will come to know whether the placement that we have done or not is reasonable. Okay, so based on the numbers, based on the frequency, or based on the specifications that has been given to us, and we'll also note down some specifications. So based on the specifications, we have to check whether this placement condition is meeting those specifications. If not, then we have to see what we can do, because if it doesn't meets at this stage, it's bound to get bad when we go to further stages of placement and route, or basically route stage. Okay, so let's try to do the setup timing analysis for idle clocks in the next video. Thank you.